My name's Lori Cook, and I'm the Manager of Educational Outreach with the American Wood Council. Michelle Cambaron is going to be joining us later. Our topic today is a wood shear wall seismic and wind design example per the 2018 Wood Frame Construction Manual and the 2015 Special Design Provisions for Wind and Seismic. Skim through the copyright and the course description and learning objectives. I'm going to assume that you all saw those when you signed up for the class. Here's our organization or outline of how today's webinar is going to be structured. We'll start with some brief references where the IBC and IRC recognize the WFCM and the special design provisions for wind and seismic, which you might hear me refer to as SPDWS. And then we'll do some design examples. First, I'll do the wind design examples using both of those standards, followed by Michelle taking the seismic examples and presenting those again with both of the standards. And then if we've got enough time at the end, we'll talk about some shear wall detailing, and then we'll have time for Q&A at the end as well. So the 2018 Wood Frame Construction Manual for 1 and 2 family dwellings is the full title of this document, and it is referenced in both 2018 IRC and IBC. And the IRC reference can be found in 30111. So you can see it's referenced by name there, which makes sense as both of those are resident. It has 1 and 2 family dwellings in the title of the complete title of the document. It can be used in IBC designs, however. So if you go into IBC section 23021, you'll see that there are some design requirements, and it refers you further to 2309. So if you have a building that is in risk category 1 or 2, it can be designed using the Wood Frame Construction Manual. So it does specify that the building needs to be within the requirements of section 113 of the WFCM. And if you go into that section, this is essentially what it points you to, the applicability limitations of the document. So you'll see that there are limits on the building dimensions, so the mean roof height, the number of stories, and the length and width of the building in plan. Additionally, there's limits on the loads that are used in the development of many of these tables and other provisions in the document. So the WFCM is kind of used to design a, just kind of an ordinary rectangular wood building. It is used for floor live loads, 30 to 40 PSF, which are very typical of residential loads. The snow loads you see that can be accommodated up to 70 pounds per square foot as well. For lateral loads, it has provisions for wind loads and seismic loads. For wind loads, it'll accommodate a wind speed of 3-second gust speed up to 195 miles per hour, which will take care of just about anything in the United States. It also can be used for exposures B, C, and D. For seismic loads, it can be used for seismic design category A through D. The IRC does have further subdivisions of D0, D1, and D2, so that's what you see referenced in the seismic design category cell on the table there. In terms of non-residential construction, the applications for the WFCM, it would be a great time saver for something like a single-story slab-on-grade structure that's length and width are less than 80 feet. So something like a commercial or retail structure, restaurants or office buildings would be something that you could use the WFCM for. And you can use it not only for the lateral designs, but also the gravity designs. and it can save you a lot of time in your design phase of your structure. So it can be very helpful in that. Here's the table of contents for the WFCM. You'll see it has 3 chapters. We've already looked at chapter 1 a little bit, which is the general information, the scoping of the structures that can be designed with this document. Chapters 2 and 3 provide parallel paths of design. They are either an engineered design, which can be found in chapter 2, or prescriptive design, which is in chapter 3. There are some differences in these design provisions, as you might have guessed, based on the titles, but you can use either of them and design a fully code compliant structure. In terms of the load references, the 2018 WFCM references ASCE 716, which is for wind and seismic design provisions. So that's an updated reference from the previous edition of the wood frame construction manual. The 2015 special design provision for wind and seismic is referenced in the 2018 IBC. This has not been, an update of this has not been released, so the 2015 edition is the most current edition of this document. And SDPWS can be used, it's an engineered design for both residential and non-residential structures. It can be used for both ASD and LRFD designs, and the wood frame construction manual can only be used for ASD designs. So depending on your design needs, this can give you additional flexibility. It has 3 different provisions for shear wall design: segmented shear walls, perforated shear walls, and forced transfer around openings. When we get into the wood frame construction manual, we'll see that that only has segmented and perforated shear wall design provisions. If you're looking for the specific language where IBC references SDPWS, you can see it here in 2305, 2306, and 2307 from the IBC. And then again, in the 2018 IBC, it references ASCE 716 for the minimum design loads for buildings and other structures. A key portion of the ASCE 7 is chapter 14, and this contains reference documents, and you can see the text here shows the reference documents for wood in the ASCE 716. So SDPWS is included in that reference in 1451 there. In terms of the background and assumptions, we're going to talk about 2 different types of shear wall design today. We're going to talk about a segmented method, which relies on individual full height segments. So you can see for this wall here that's been highlighted, we have 3 full height segments. They're varying widths, but they all have it in common that they run the full height of that wall uninterrupted by an opening. Each of these segments will have hold downs at the end of each segment, which you can see here, these dark black lines at the bottom of each of these segments here. So with this type of design, you would have the maximum number of hold downs present. And you also are neglecting the contribution if you're sheathing above and below the opening. You're neglecting the contribution of the sheathing around that opening. So if you're planning on sheathing the entire wall as part of your construction, you can use a perforated shear wall method like this, where you assume that the entire wall is sheathed except for your window or door openings, and then you only have hold downs at the ends of the wall. This allows for a more efficient structure in that you're using the contribution above and below the window openings here that is being provided by the sheathing on that. So here we have our second poll. So I'll let Marcy go ahead and launch that.
Yes, indeed. All right, so WFCM prescriptive provisions include which of the following? 110 to 195 mile per hour wind loads, exposures B and C, segmented and perforated shear walls, or all of the above?
The answer is all of the above. So we had nearly everybody get that, so that's great. All right, and we'll keep rolling then. So we're going to go now into the wind design examples. So the first one I'll do will be the 2018 WFCM prescriptive approach. And as you might guess by the name, this is the most prescriptive, and it provides the simplest design approach, the least amount of actual number crunching. A slightly more number intensive approach would then be the second approach we're going to use, is the 2018 WFCM engineered. And then the most engineering intensive approach would be the third approach, which we'll look at, which will be the 2015 special design provisions for wind and seismic. So let's start again with the WFCM prescriptive. That's going to be chapter 3. And when we go to the beginning of chapter 3, we see these prescriptive design limitations. Again, the building geometry is unchanged from what we saw in chapter 1. We have limits on the wind exposures that when we're in chapter 3, we are limited to exposure B and C. If we go into an exposure D, we can design for that using the engineered approach in chapter 2. It does have approaches for both segmented and perforated shear walls in chapter 3, and then we saw some of the other application limits in the slide before this. For the WFCM designs, they're all based on what's kind of known as this baseline wall, and it's described in this slide here. So it's a shear wall with stud space at 16 inches on center, and the sheathing is assumed to be a 3/8 inch wood structural panel on the exterior, attached with 8D common nails, and they're spaced at 6 inches on center at the panel edges and 12 inches on center in the field. The interior of that wall is assumed to have 1/2 inch gypsum wallboard that's attached with 5D cooler nails, and the spacing is 7 inches on center at the edges and 10 inches on center in the field. So this is kind of the baseline wall that the WFCM tables were developed with in mind. So using that, we can see that we do actually have one other thing we need to pay attention to, and that's in table 317D. There is a reference to the maximum aspect ratio for shear wall segments being 2:1. Footnote 4 does allow the aspect ratio to be modified up to 3.5 to 1, but it requires an adjustment per SPDWS. So in 2018, this is the first time that we've seen it actually both apply to both seismic and wind. So this is the one adjustment that we'll see applied using 2BS over H from the exception here in 43341. So this 2BS over H is modified. It's applied to the shear capacity of the wall, and we'll use that to modify our design later. So be aware of that. So for this design example, we're going to design the first floor shear wall, and you can see the total length of this wall is 36 feet. If we go on to the next slide, we see some other pertinent information about the structure. We're assuming it's 130 mile per hour exposure B, wind exposure. We said the wall we're designing is 36 feet long. The wall that is perpendicular to that is 30 feet. So that's an important value that we're going to need for some of our designs. Our top plate to ridge height is 6.25 feet. And this is a 2-story structure. So there's a floor on top of the floor we're going to be designing today. We're assuming our wall heights are 8 feet, and then our door and window heights are 6 feet 8 and 4 feet respectively. we're assuming we've got a wood structural panel exterior sheathing, and for our design today, we're actually going to use 7/16 inch thick panels. We're going to check both with and without the contribution of the interior gypsum. Now, because this is a wind design, we are permitted by code to allow the gypsum to have some contribution in our shear wall design. That's something that we don't get to apply in a seismic design, but again, since this is a wind design, we do get to take advantage of that. And we're going to neglect deflection in this example. So the first thing we do on the prescriptive approach is go into table 317A. And this gives the length requirements for full height sheathing in segmented shear walls. So we have a tabulated wind speeds. Unfortunately, the top part that had the wind speeds got a little chopped off here, but the column we're using, this is the 130 mile per hour gust column. So you have one for every, just about every wind contour you might need. We have tables here for exposure B, that's what our building is in, but we do have tables for exposure C as well. So the title of this table is shows the segmented shear wall sheathing requirements, and then below that it tells you that you need to apply the load to the wall that is perpendicular to the wall in question. So for us, that's the wall that's 30 feet in length, or the short length of the building. So we're in the wall that is supporting one floor above it and a roof. So using the interpolation between 28 and 32, because our wall is 30 feet, we get 12.9 feet. We're going to adjust that using footnote 4 here in table 317A, and that allows us to adjust it based on the fact that our wall height is only 8 feet instead of 10 feet, which is assumed in the table. And also we had a shorter top plate to ridge height. Ours was only 6.25 feet. So doing a double interpolation there, we are able to adjust that 12.9 feet down to 8.8 feet. So that's the length of full height sheathing we need for our structure, for our wall design. So in this design, for the sake of simplicity, we could have used 3 panels and just had one on either side of the door, but for the sake of symmetry and just for the sake of ease of construction, for this example, we've specified 4 full height panels that are all 4 feet wide and 8 feet long, so they meet that 2-to-1 aspect ratio requirement. So we're providing 16 feet of full height sheathing, so we're good. We meet that 8.8. Now, if we go into table 317D, this gives us information on the unit shear capacities of our assemblies, and it also gives us this sheathing type adjustment factor. So if we go into here and we take a look at the exterior wall sheathing that's noted in the gray, and then below it in the white is the interior wall sheathing. So again, remember that we said we were using the 1/2-inch gypsum wallboard, and the maximum shear wall aspect ratio is 3.5 to 1. So we're less than that. And then the sheathing type adjustment factor is equal to 1.0. So if we neglect the contribution of the sheathing, we would then go into the top row of this part here, of this cell, and we see that our sheathing type adjustment factor changes to 1.3. So what does that mean? Well, that means we multiply our full height sheathing requirement, that 8.8, by this sheathing type adjustment factor. So then we see that our required length is 11.4 feet. All right, sorry, there we go. My PowerPoint was a little stuck. Okay, so assuming again we're using the 4 full height panels that are all 4 feet wide, we're providing 16 feet of full height sheathing. And again, this exceeds the 11.4 feet that is required, so our design is okay. Since this is a segmented approach, we would need to supply hold downs on each segment, and we're going to calculate the required capacity of those in just a bit here. But again, our design summary is we've provided 7/16 thick wood structural panel exterior on the exterior with the 8D common nails, and then the 1/2-inch gypsum wall board with 5D cooler nails on the interior. So if we wanted to do a perforated shear wall, if we are going to be sheathing the entire wall surface, we start with that same segmented shear wall full height sheathing requirement. So in our case, that was that 8.8 feet that we calculated for the wall with the blocked gypsum on the inside. So dividing that by the total wall length, which is 36 feet, we see that that is 24.4% of the actual wall length. So using this table here, table 317E, we interpolate and we see that our perforated shear wall length increase factor is 1.83. So multiplying that by the full height sheathing requirement from the segmented shear wall, we see that we need to provide 16.1 feet of effective full height sheathing if we're using the blocked gypsum on the interior. If we're not supplying the contribution of the gypsum interior, then we would do the same equation, the same calculations, but we start with 11.4 feet and we see that we need 19.3 feet of full height sheathing. If we look at the illustration of the wall, if we go back to when we were looking at it where it had the all the full dimensions on it, we see that we're supplying 21 feet of full height sheathing, and all of our segments are within that 3.5 to 1 maximum aspect ratio. So we supplied 21 feet of full height sheathing. That's greater than both 16.1 feet and 19.3 feet. So our perforated shear wall meets the requirements, and we need hold downs only at the ends of the wall. So for the prescriptive approach for the WFCM, our hold downs for segmented and perforated shear walls are calculated the same way. We go into this table 317F here, and we see that for an 8-foot wall height, we, for a wind design, have a required hold down capacity of 3,488 pounds. That's based on the first shear wall panel capacity. So if we have a lower capacity wall, for example, a wall that doesn't have gypsum on the interior, we can divide that value from the table by the sheathing type adjustment factor, and we can see that for the wall without the gypsum on the interior, our hold down capacity is only 2,683 pounds. Bearing in mind that this is a first floor shear wall capacity requirement, we would need to combine this with any top floor hold down requirements that we calculate for the second floor of the structure. And again, this is based on the capacity of the first shear wall panel. So that's why it doesn't matter if it's a segmented approach, doesn't matter if it's a perforated approach. It's based on the actual physical capacity of that wall panel. For chapter 3, for the prescriptive chapter, we don't include any sort of dead load offset. So if you went into chapter 2, the WFCM engineered approach, we'll see a similar table up front that shows the engineer design structure limitations. One thing that I mentioned earlier is that if you're in an exposure D category for wind, you can use chapter 2 for that. If we start in table 2.5b, this will help us determine the loads on the structure. So we see that we can calculate based on our roof pitch as well as the roof span. So for us, we're calculating the length, the L dimension, this wall. So we would use the B dimension for the table based on how you're supposed to apply this table. So our distance would be 30 feet that we would interpolate, and then we have 130 mile per hour gust as our wind speed. So we interpolate these values and we get a value on the roof of 94 pounds per lineal foot. The floor load is 128 pounds per lineal foot, but we do have a footnote we can apply. So footnote 2 allows us to apply an adjustment based on the wall height. So we are able to reduce the floor load by nearly 20% there. So our total shear load is 199 pounds per lineal foot times that 30-foot wall surface it's applied to. Divide that by 2 because there are 2 shear walls. There's one on each side of the house, and our applied load on that wall is 2,985 pounds. And that's the load that's applied at the top of the first floor shear wall. We go back into table 317D. We're going to pay attention to some slightly different columns this time around. We're still looking at our exterior wall sheathing that's in the gray. So again, we went with the 7/16 panels for this one. And we're going to look at both the no sheathing and then the gypsum wall board on the interior. And if we look at the unit shear capacities of these assemblies, we can take a look. We see that the 7/16 wood structural panel has a capacity of 336 pounds per lineal foot. The gypsum has a capacity of 100 pounds per lineal foot, which gives us a total of 436 for the combined wall. Dividing the resistance by the capacity, or the capacity by the resistance rather, we see that we have a required full height sheathing length of 6.8 feet for the wall with the block gypsum interior, and then 8.9 feet if we're not including the contribution of the gypsum. So if we sharpen our pencils and do a little bit of number crunching, we see for the wall with the interior block gypsum, we only need 2 full height segments on the ends here rather than the 4 that we had applied before. For the design with no interior gypsum, again, we could, apply just 1 full height segment and meet the requirements, but for ease of construction, we'll probably just do the 4 full height segments there. All right, but let's say we're gonna sheathe the entire wall once again, so we want to do a perforated design approach. The approach that's described in chapter 2 of the WFCM reference is the SPIDWIS capacities and adjustments. So if we look at our wall capacities, again, we were able to see that it was 436 pounds per lineal foot for the wall that used the block gypsum interior. And then it was 336 pounds per lineal foot for the wall without gypsum. The applied load is still 2,985 pounds. That has not changed. So we calculate the percent of the wall that is full height sheathing. So it's based on the effective full height sheathing. So in this case, what we need to do is we need to adjust the resistance based on those high aspect ratio segments. So the high aspect ratio segments were those long skinny ones that were between the windows, and we need to adjust them per the SPIDWIS 4343 adjustment that we see here, this 2BS over H. So that's what this you see here, this 2 times 2.5 divided by 8 is that adjustment. And we multiply that by the the length of that segment, which is 2.5 feet. And then we'll add that to the 16 feet, which is the four 4-foot full height segments that were on either end of the wall and on either side of the door opening. So that gives us an effective full height length of 19.1 feet. Divided by the total wall length of 36 feet gives us a full height sheathing percentage of 53%. Using this table 4335 from SPIDWIS, we get a shear capacity adjustment factor that we are able to interpolate, and it's equal to 0.59. So we multiply that by the capacity of the wall. So for the wall with block gypsum, that capacity was 436 pounds per linear foot. So our adjusted wall capacity is 257 pounds per linear foot. Divide the demand by the capacity, and we see that we're required to provide 11.6 feet of full height sheathing, which is less than that 21 feet that we are providing, so we're good, and that's for the wall with the block gypsum. We run the same calculation for the wall without gypsum. We see that we're required to provide 15.1 feet of full height sheathing, which is still less than the 21 feet that we're providing, so we're okay. So this is what our first floor shear wall would look like. Our 19.1 feet of effective full height sheathing is greater than that 15.1 feet. The exterior of the wall would be 7/16 wood structural panel with the 8D common nails. Again, the spacing is 6 inches on the edge and 12 inches in the field. The gypsum wallboard interior is attached with the 5D cooler nails at 7 inches on center at the edge and 10 inches on center in the field. The hold downs for the engineered chapter, these are calculated the same way that the table in chapter 3 was calculated. So these numbers are probably going to look familiar to you. The capacity of the wall is what still controls the design. So we would need to base it on the wall capacity depending on whether or not we're using the gypsum interior. So for our wall with the gypsum, the capacity of the hold down is 3,488 pounds as a minimum. Without the gypsum, it would be 2,688. And again, we have the same notes for combining it with the top floor hold down requirements. You can account for dead load offset in chapter 2. There is some language that will allow for that in 224. We did not do it in this example, but you are allowed to do it if you're using chapter 2. All right, so the next thing we're going to do is going to jump into our next poll. So Marcy's going to read that for us.
Yes, I am. The WFCM tabulated hold down capacity requirements are based on capacity of the first shear wall panel. Don't account for dead load unless specified by designer, are cumulative with floors above, or all of the above.
They are. So the majority got it right there. It is D, all of the above. So
Excellent.
Good for everybody that got that. All right. So the last wind example we're going to do today is going to be from the 2015 Special Design Provisions for Wind and Seismic. So there is a slight difference in how the tabulated values are presented, and you might notice that when you look at these numbers here. So in SPIDWIS, the capacities are presented in a nominal fashion. So to convert them to an ASD basis, which would be, so we'd have a same apples to apples comparison, if you will, on the design from the WFCM, we divide these capacities by 2. There's a different way you would convert them if you were doing an LRFD design, and that's all specified in SPIDWIS, so you can take a look in there if you have further questions. But so anything for an ASD design that's in these tables in table 4.3a, and also we're going to look at table 4.3c, For our gypsum wallboard capacity, we divide that by 2, and we get our ASD capacity, which is 100 pounds per lineal foot for the gypsum wallboard. So the capacities in the wood frame construction manual were 336 and 100, and in SPDWS they're 335 and 100. So there's a slight rounding difference, but they're essentially the same capacity. We do want to make sure that we are within the maximum shear wall aspect ratios. So for our wood structural panel shear wall, we meet that. We're within that 3.5 to 1 aspect ratio. We do need to pay attention again to the shear wall adjustment factor, the capacity adjustment factor. So there's the one from section 43341, the exception, and this is the adjustment based on stiffness. There's also an adjustment factor for the aspect ratio based on strength. So we will take a look at both of these in our design, and we don't need to apply both of them simultaneously, but we do need to choose whichever one is more conservative. So if we look at our required capacity, that hasn't changed from the WFCM example. So it's 2,985 pounds is the demand. For the wood structural panel side of the wall, we assume that it's 335 pounds per lineal foot for the exterior capacity, and then 100 PLF for the gypsum on the interior. The total would be 435 PLF. So for a segmented approach, we see that we need 6.9 feet of full height segments if we have block gypsum, or 8.9 feet without the gypsum. And these numbers probably look familiar to you based on the WFCM example, and that's because they are the basis of what the WFCM provisions are developed on. So for the SPDWS example, we did take a look at this higher aspect ratio segment to meet our full height segment demands. So we have 2 kind of tall, skinny segments between the windows here that are 2.5 feet wide, and we would need to adjust them based on those high aspect ratio adjustment factors we took a look at. So this is the first one, which would be SPDWS 43341, exception 1. And for those high aspect ratios, we multiply the width of the segment, the B value, times 2BS over H, and that gives us our effective full height sheathing length, which is 11.1 feet, which is still greater than the 8.9 feet that's required, so we're okay. And if you're assuming the no interior gypsum, again, if you're using the other high capacity aspect ratio adjustment, that's per SPDWS 4342, you would apply the 0.6, but multiply that by the 2.5 feet of the high aspect ratio segments, and this gives you a value of 11 feet. So this would be the one that applies, as it's more conservative, but it's still greater than the 8.9 feet, so we're okay with that. If we wanted to do a perforated shear wall design, we're going to calculate a shear capacity adjustment factor, which is from equation 4.3-5 rather. So this is the C sub O that we used the table for in the previous example from the WFCM in the engineered approach. So the calculation of L sub I is the same. That high aspect ratio segments are being adjusted, having their capacity adjusted by this 2BS over H value from SPDWS 4343. So that's why you see this adjustment applied here. So our total wall length is 36 feet, and then this A sub O value is the area of the openings. It's the actual opening area for the entire wall. We calculate these based on the equations that are in SPDWS, and we get a C sub O of 0.77, which is substantially higher than what we calculated when we used the tabulated values that were in the WFCM example. So by having this higher C sub O value, it's a smaller reduction in our design capacities, or so our wall capacity for the wall with the block gypsum is adjusted down to 335 pounds per lineal foot, and we're only required to have 8.9 feet of full height effective sheathing. Without gypsum, we run a similar adjustment, a similar capacity calculation, and we see that we need 11.6 feet of full height effective sheathing length. So looking at our wall, we're providing 19.1 feet, which is greater than both the 11.6 value and the 8.9 value. So we're good on that. We can calculate our hold down capacities now. So if we're calculating our hold downs for a segmented design, it uses this T equals the shear times the shear wall height. So it's based on the actual induced unit shear, as opposed to the WFCM, which it was based on the wall capacity. So for our wall with the block gypsum on the interior, we have our induced unit shear that we calculate. So our shear wall hold down capacity is required to be 2,985 pounds. Running the same calculation on the shear wall without the gypsum, we see 1,840. So those are substantially lower than the capacities that we have calculated with the wood frame construction manual. That's because these are based on the induced unit shear, on the actual load, not the wall capacity. There's also language in SPDWS to account for dead load offset. If you do want to use that, that's allowed. We neglected it in this example. And again, you'd need to combine it with the top floor hold down requirements from the second floor. For the perforated shear wall, we calculate the hold down capacity using equation 4.3-8 here, and it uses that C sub O value that we calculated, or you can use it, the value that you got from the table 4335 if you use the tabulated approach. You see our hold down capacity that's calculated here is 1,624 pounds. See, we have the same caveats as we saw on the previous slide, so I won't bore you to death with those just again. This is our summary slide for our wind design examples. So the numbers, the first numbers you see are the heights, the required full height sheathing for the walls with the gypsum interior contribution. The numbers that would be the heights next to it are in the brackets, would be the wall without the interior gypsum. Our nailing schedule didn't change for any of our walls. They were all 6 inches panel edge spacing and 12 inches in the field. And then you can see the hold down capacity requirements depending on if you were using the segmented shear wall for SPDWS or the perforated shear wall. And then it was the same regardless of your approach with the WFCM. So that's all of our wind examples. We'll go ahead and give it over to Michelle now, and she can walk us through some seismic examples as well as some shear wall detailing.
Great, thank you, Lori. And hopefully all of you are seeing my presentation. Let me do this and get the audience sharing view. Great. A lot of good questions coming in, and Lori will now monitor the questions that are coming in, and then we'll follow up with a Q&A at the end of the webinar. As Lori mentioned, I'll be doing the seismic design example, going through the 3 different approaches, the prescriptive, engineered, and using the wood frame construction manual, and the wind and seismic provisions, or the special design provisions for wind and seismic. I won't go into as much detail as Lori has gone into because she's covered much of the methodology going through this. What I will do is go through and point out the differences when we're doing a seismic design. But in your handout, you have a complete wind design approach and a complete seismic design. So there is a little bit of duplication, but we wanted you to provide you with a complete design in your handout. Let me go here. Okay, so one difference that we have here is obviously we're going to be designing for seismic, and we'll be designing for seismic design category D1. And then we will assume a 7/16 inch wood structural panel. Wood structural panel includes both plywood and OSB. And then our framing is spruce pine fir with a specific gravity of 0.42. We have a ground snow load that's 30 pounds per square foot. And then we have the dead loads of 25 for the roof, ceiling, attic area, the dead floor load of 12, partition load of 8, and wall of 110 pounds per linear foot. And our aspect ratio of our footprint of our building is L over W, which is 1.2. So sorry about that. And the whole configuration of the building is the same as what Lori designed. So that's what's nice about this design example is we're doing a side-by-side comparison of a wind to seismic. Okay. And more important is the dead load and the snow load and how that plays into the overall design when we're dealing with seismic. Seismic obviously equals the force, mass times acceleration, and we'll be designing these first floor shear walls. There was a question that came in that stated, shouldn't the second floor shear walls be designed? That is true. The second floor shear walls should be designed, and you carry that down into the first floor. But for time, since we're limited on time, we're designing the first floor and taking all the load from above and putting it into the second floor to design our first floor shear walls. Now, so we'll get into the prescriptive approach. And as was mentioned previously, the wood frame construction manual, we can use it to design for seismic design category A and D, and then segmented and perforated shear walls. Force transfer around openings will need to be done using the wind and seismic provisions. Lori went through all the applicable limitations which this project meets, and one thing that I do want to point out is the seismic load criteria, and we can do A, B, C, and D seismic design category. For those of you that are not familiar with the residential IRC building code, then what D0, D1, and D2 are, it's just a subcategory of seismic design D. And so this is just fine-tuning the calculations into 3 subcategories of seismic design D. And this becomes really relevant when we're dealing, say, track housing, and we're using that same design over and over and over throughout the track housing. You can find some efficiencies in your design by going into these subcategories rather than just doing it all for seismic design category D. And then we meet the prescriptive design limitations, which Lori went over previously as well. So right off the bat, this is our baseline of construction when we're designing for seismic loads. And it's keys into the table 317C. That's where we go to get our capacities of our shear walls or our length reductions of our shear walls. And the tabulated values assume wall studs are spaced at 16 inches on center. We have 3/8 wood structural panel, but we're assuming 7/16. And then we have 8 penny common nails at 6 inches on center, 12 inches on center for field nailing. So this is the baseline shear wall that we are using in all of our design for seismic. And it's very similar to wind design, except that the wind design includes gypsum, is some minimal criteria in when Lori was looking at this section. And I can't remember the criteria, but it's in that same section. So right off the bat, we have ground snow load of 30 pounds per square foot. We are starting off with our segmented shear wall, and we have this dead load of 15 pounds per square foot for the roof ceiling. Floor is 12 pounds per square foot. Partitions is 8, and then walls is 110 pounds per linear foot. And we have seismic design category D sub 1. This is just a truncated table. We also cover D0, D1, and D2. We have our aspect ratio of 1.2. And so our width of our building is 30 feet. And because we don't align with this specific rows and columns here, we need to do some interpolation, linear interpolation. So we come up with 15.8. That is our required full height sheathing that's required for our segmented approach. And one thing I wanted to note is that for the ground snow load, we have 30 pounds per square foot. We also have tables for 50 pounds per square foot and 70 pounds per square foot. And the code requires, and I can't remember the section, but it does require in Chapter 16 that if you have ground snow load greater than 30 pounds per square foot, you need to include 20% of the ground snow load. So the other tables that are 50 and 70, they include that 20% in the grounds in the table. So they account for that in the lengths that are required. And here we go to our table, and note that the table was based on 15 pounds per square foot. And you can see this by looking here in this column. Here's the 15 pounds per square foot, 12 floor, 8 partition, wall is 110 pounds per linear foot, and there's 1.0. So this is our adjustment factor from the previous table. And then from there, we notice that, wait, we have 25 pounds per square foot. So since we have 25 pounds per square foot, we've got to adjust our length required based on that additional weight. We have more weight, that means more seismic load. So we can use this handy dandy table and see that we have to increase, now based on the W and linear interpolation, we have to increase our length by 20% because of that additional load. So this is a really cool table because you can utilize the previous table for all different kinds of weights, and you can easily adjust the length required. Oh, by the way, the section related to the snow load requirement is in the IBC footnote 5, section 1605.3.1. That's where it talks about increasing your load if you're greater than 30 pounds per square foot snow load. Okay, so we adjusted our 15.8 by 20% and we get 19 feet. That's our required length of full height shear wall. So we go to our table, table 17.317D. And this is a table that you use for both wind and seismic. And you can see the gray area is the exterior sheeting, as Lori mentioned, and the white is the interior. So we're starting off, we have our seismic column, and we have no sheeting on the inside, and we're not counting on gypsum. We just can't account for that for our seismic design. So here we would multiply our length times 1.0. Now, one thing to note is if we didn't have enough capacity, if we put wood structural panel on the inside here, we multiply times 0.5, and that means we have double-sided shear wall, and we half the amount of length required from the table. And that makes sense because we're providing half the amount, double the amount of shear wall. So then we'd do 0.5 times our length, but we have 1, so we are just the straight length that's required. Now, the aspect ratio, Lori went over this previously, but the same thing is we are at 2:1. If we're greater than 2:1, then we need to adjust it based on the wind and seismic provisions by 2B over H. And so we look at, and here's a section straight from the wind and seismic provision that states this. And this has to do with shear wall stiffness. So we want to have the shear walls deflect the same amount. We don't want to have incompatibility of that deflection, and we want to have that drift all the same along that line. So, and that has to do with stiffness. So some of our walls exceed that 2-to-1 ratio, and we have to reduce that. We have to increase the length requirement for those shorter shear walls. So the actual length is 21 feet, adding all those lengths up. And then we have include our adjustment factor, and our effective length is 19.1, which is greater than 19, which was the required. And then so we're good to go. You could actually do 3/8, but we're doing 7/16 wood structural panel, 8 penny commons at 6 and 12. So that's the segmented, and the perforated, and then the hold down's full height, segmented. Then we go to the perforated. Nothing is different from this design approach between the wind and the seismic, so I'm not going to go into detail here because Lori did a really good job of covering this whole process. And I'll just skip forward and get the results. The advantage of having those going to a perforated shear wall methods is it eliminates the need for full height. It eliminates the need for hold downs at each full height segment. The hold downs are designed the same as what Lori had designed. So here we go. Here's a quiz or poll that does not count towards your certificate. And I'll bring in Marcy.
Absolutely. And thank you again for reminding them that this does not count toward their certificate. So WFCM seismic tabulated shear wall values assume which of the following: that studs are spaced at 16-inch on center max, 3/8 inch wood structural panels on the exterior, 8D common nails at 6-inch on center panel edges, or all of the above.
It is all of the above. Great. Thanks for participating in a poll. Okay, now we'll look at the engineered approach using the wood frame. Oops, I skipped through quickly. The engineered approach, we have our engineered design limitations, which Lori went over, and we meet all that criteria. And then here is where we determine what our lateral loads are. So we know seismic load is based on the dead load of the building. And here we come up with our actual dead load for the actual building that we are designing. Now, when we do the dead load, we take all the second floor, roof, walls, interior partitions, and then the floor, and then we take half the height of the wall, first floor wall, and include that in our weight. So when we did all that calculations, we get a total weight of 83,680. That's the weight of the building. And then we get our seismic force, which comes from this equation. And that becomes 8,228. Now, I'll explain this in the next slide because it's better. It shows graphically what I'm talking about when we do our seismic design. So the wood frame construction manual utilizes the simplified approach per ASCE 716, and that's in section 12.14.8. And in the commentary of the wood frame construction manual, it goes into detail, step by step, on how this approach is incorporated into the wood frame construction manual. Incorporates the vertical force distribution factor, and then the design 5% dampening, spectral response accelerator, parameter factor, and then, parameter at short periods. And then it also incorporates the seismic response modification coefficient. So all of that is incorporated in the equation that's shown here for the second floor and the first floor. And then you can have 3 stories based on the criteria of the wood frame construction manual. So there's no black box. It's per ASTM 716, or I'm sorry, ASCE 716. Okay, once we get our design load or our demand on our building, we have our table we go back to, which is 317D. And now instead of doing a sheathing adjustment factor to adjust the length, we look at what is the capacity of our shear wall. So our unit shear capacity, based on the exterior being the 7/16" wood structural panel and the nailing, baseline nailing, no gypsum, no interior sheeting, we have 239 pounds per linear foot. So that's the capacity of our shear wall. And we still have to adhere to the aspect ratio adjustments as well. So that's the stiffness adjustment based on 2B over H. So we have our required capacity. First, the demand on that building is, the whole building is 8,228. And then we divide that by 2 because we have 2 lines of resistance, 2 shear wall lines. So we have 4,114. And then our capacity, as mentioned previously, is 239 pounds per linear foot. So we have 17.2 feet required just based on the baseline shear wall capacity for the full height shear wall. And we're doing the segmented approach. And then, so we do it, we're trying to do the same approach that we did in the prescriptive, where we're looking at the lengths of the shear wall. So we adjust our actual shear wall lengths to take into account that aspect ratio for the shorter walls. And we have actual length or effective length of 19.1, which is greater than the required of 17.2. So we're good to go. And baseline nailing of 6 and 12 with 8 penny common. Then I won't go through the perforated shear wall approach because it's the same process, just different numbers, nothing different from seismic, just the process is the same. And going from there. So I'm going to go forward. You always, if you are going to have a perforated shear wall approach, you always have to do the segmented first to get to the perforated shear wall approach. And we are basing, in the wood frame construction manual, we're basing it off of the larger opening, which is based off of that 6'8" door. And we're not taking into account all the smaller openings. We're assuming every single opening in that wall is the 6'8". And that's the conservative approach to using these tables. Whereas Lori went through and fine-tuned it in the wind and seismic provision design. And so we're kind of penalizing the perforated shear wall because we're basing it off of that one larger opening that at each of the openings. And so we get our results, and I'm going to skip this because I want to get into the details, or well, why don't we do it, Marcy?
Okay. Here we go. The tabulated perforated shear wall's shear capacity adjustment factor is based on the maximum unrestrained opening height. Is that true or false?
And the answer is true. If you recall, and I think Lori went over this, let me go back to this. We are basing our perforated shear wall on the door opening, rather taking into account each of the smaller openings and the door opening. We're assuming all the openings are the size of the door. And so that's a conservative approach, which is shown here. So we're taking this large opening and saying all the openings are that size. Okay, so now we're going to get into the wind and seismic provisions, and we know that we can use this for an engineered design, residential, non-residential, does ASD and LRFD design, and we have we can do also force transfer around openings utilizing the wind and seismic provisions. The other thing I want to point out is you can use the wood frame construction manual and then supplement it with designs using the special design provisions for wind and seismic. So if you want to get an overall design and then find some efficiencies in your design using the wind and seismic, that's perfectly fine. As Lori pointed out, the materials chapter in ASC 716 related to wood, and that they reference the AWC NDS and wind and seismic provisions. So we're going to start off, and this is where we're going to find some efficiencies in our design when we determine our capacity of our shear wall. We have the wood structural panel, and this is a nominal shear wall capacity table. We have 7/16, but we can find some increased efficiencies in our design by taking into account, well, first, this is a nominal unit shear capacity, so we've got to divide it by 2 to get it into an allowable stress design. Then, because we have our studs at 16 inches on center, we are allowed to take the value for 15/32 per footnote 2. So that bumps it up from 480 to 520. Then we've got to adjust based on the specific gravity, because the tables are based on southern pine or Douglas fir, and we have spruce pine fir, so we get a little bit of reduction, 8% reduction in our capacity. Not a lot, but just a little. We still got to adjust for that. So we go 520 pounds per linear foot times 0.92 and divide by 2 to get an allowable stress design, and we're at 239 pounds per linear foot. And then we've got to look at the adjustment factors based on stiffness, which we talked about previously, 4.3.4.1, and then based on strength, which is what this table is about, table 4.3.4, and is explained in the next slide, where we're adjusting for strength. So the previous section was so that we can have equal deflection in our shear walls, so we have drift compatibility. And the other one is, this section shown here is based on strength, because the narrower wall is going to be less strong than the longer wall. Now, these are not cumulative adjustments. There's whichever one the least would govern in the design. So remember, we have our wood structural panels at 239 pounds per linear foot. We're going to compare the adjustments. One is based on stiffness, which is the 2B over H, and that it comes out to be 0.62. The strength reduction is going to be based on, or adjustment is 0.84. So the governing adjustment is 0.62. More often than not, the stiffness one is going to govern when you compare the two adjustments, but either way you have to check the two. And so when we do that, we are reduced to 149 pounds per linear foot based on the stiffness. Now that's just for the walls that did not meet the aspect ratio of 2:1. And that's for both cases, checking for stiffness or strength. So we come up with our capacity adjustment. It's still greater than what our required capacity is, so we're good to go. And in order to compare apples to apples, we also look at adjusting our length, and just to have apples to apples on length required. So our length required was 17. We have an actual of 21. Okay, so here Lori went into detail by fine-tuning her design in the perforated shear wall approach, where instead of taking the largest opening, we are now adjusting, finding the shear capacity adjustment factor based on all the sizes of the openings, and finding efficiencies there. So I won't go into that detail because Lori went into detail, but it's a reiterative process to fine-tune the calculations. Okay, so there, I'll fast forward a little bit and get into some details because the process is the same. But before I get into some details, I want to show you a side-by-side comparison between the wind design and the seismic design. And as you can see, the seismic design is what governed, because this shows you the length that's required for the shear walls and the nailing that's required. And the ones you can see that are in brackets are with drywall, or maybe it's the other way around. Yeah, the one in brackets are with drywall. So we have the prescriptive approach and the wind design. You can see that the engineered wood frame construction manual approach is very similar, if not exact, to the wind and seismic provisions shown here. And this is finding a little bit more efficiency based on finding that shear adjustment factor by taking into account all the opening sizes rather than base it on the large opening. And then seismic, you can see we have more demand, more length required, and we are equal to the engineered approach from the wind and seismic provision here and here. Now you notice the nailing is a little bit more or less for the wind and seismic provisions. We have 4 and 12 versus 3 and 12. And that's similar to, we have more length in the wood frame construction manual for the wind design, for the engineered approach. And then we have less length required for the wind and seismic provisions. But the nailing is the same. So it's very similar. Okay, so now I'm going to get into some detailing because we have a few more minutes. And I know we've gotten some questions regarding detail requirements and why things are the way they are. This gives some background on testing and what was seen after earthquakes, like the San Fernando earthquake, etc., that we've seen in damage from buildings in the past. And this is an example of a wood structural panel, shear wall test, cyclic test using Curie protocol. We have on the horizontal axis displacement. We have on the vertical axis load. And as the wall is, the load is applied, it deflects. And so you can see here, right at this peak here, there was a drop off, and that's where we had some failure, but we're here at about almost 3.5, which is really good. It can deflect a lot and withstand a lot of load. So that's really good. And that's one thing, you can see it rocks back and forth, and wood shear walls are pretty ductile because we have all the tiny little fasteners that allow it to move and deflect and still hold quite a bit of capacity. Where we design for is right around in this area. That's where we design for. So this shear wall is an 8x8 shear wall. We have 4x8 panels shown here and here, and there's a panel joint in the middle. And when we look at after the test was performed, the failure mode, and this is great, we want to see failure, we want to see how it fails. We can see at the panel joint, and note that there's 2 2x here that are sistered together rather than a single 2x member. So at high loaded shear walls, that's where we saw some issues in the past. When there was a single 2x member here, there was some issues with the connection of the panel in this location. And so now this has 2 2x members, but we see the yielding of the nail yielding at the adjoining panel edges. And then at the sill plate, we see nail yielding right here, the head pull through right here. And this is good that we know what the failure is. But what's great is that this is a ductile failure rather than a brittle failure, which is what we're after, especially when we're dealing with earthquake loads. So here's that adjoining panel edges where we see some racking back and forth of the shear wall and can cause issues at that panel joint. And that is why it's required to have, for high loaded shear walls, a 3x member there because of the accentuation of the forces and the racking that can occur at that panel joint. You're nailing off 2 panels here, and we want to make sure that we have the proper connection. Now here we talk about nailing. When we get closely spaced nails, we can have issues with splitting that occurs. What happens is that nail acts like a wedge and pushes those nails apart, the wood apart, causing weak perpendicular grain issues, stresses. And that's the Achilles heel of wood, is that perpendicular grain bending and stresses that can occur. So rather than having all the nails in a line, we want to stagger the nails when they're closely spaced with the grain of the wood. So instead of being in line, this nail should be here, the next one would be there, and alternating back and forth. And here, I show this slide quite a bit across the country, and almost every time there will be someone answering this wrong. So it might be a good idea to have a drawing that shows the framer what we mean by staggering of nails. So in these two pictures, some may say the one on the left, some may say the one on the right. But what we're really doing is talking about staggering those nails so they're not within the line of the grain. And I should have mentioned this is a panel joint, and then there's a framing member up and down the slide. So this is staggered, this is not staggered. And this just nails the idea home. I know, kind of a bad joke, but anyway, there's the nails. We don't want to have them in line. We want to stagger them. Okay, so go there. And then we have double-sided shear walls. This is true for both seismic and wind. See footnote 6, which is for the entire table. There's footnote 6. It's where panels are applied to both faces of the shear wall, so double-sided shear wall, and the nailing spacing is less than 6 inches on center. We need to offset those panel joints on our framing or provide a 3x. So here we go. Here's a really good graphic that shows panel joint here, panel joint here. And then where they are on the same 2x member, we need a 3x. Now you wonder, are you going to really be able to predict where that panel joint is? You may want to just specify a 3x, but in addition to a 3x, you can also specify 2 2x's. And that's noted here in these sections of the wind and seismic provision that allows for 2 2x's. In the commentary, it states what the 2 2x's need to be how they need to be connected. And then there is some additional requirements beyond the 2 2x's. And that is shown here. If 3x's are required, if your nail spacing is at 2 inches on center or 10 penny penetration more than 1.5 inches for 3 inches on center, et cetera, et cetera. And so instead of a 3x, you can also say 2 2x's. I think I misspoke. I meant when we have 2 shear walls on each side, there's also an additional requirement that may come into play, which is shown here. Okay, and then in the commentary, it also mentions about stitching the 2 2x's together. And that's key because we want to have that continuous load path through the shear wall. And this is a handy table that was developed by Phil Line, our seismic wind guru at AWC. And he developed this table just based on what's in the NDS and come up with some applicable nailing for different spacing of shear wall, nail spacing of shear walls. And I'll skip this, but there's one other thing I want to go to because we'll come back to that in the Q&A. Here's another one related to the sill plate. Now, we've had questions about 3x sill plates, and that was in the IBC, but that was never in the wind and seismic provisions. But I suspect it had to do with a failure mode that was noticed out in after earthquakes. Now what happens is for one-sided shear wall or even two-sided, what happens is when that shear wall rocks back and forth, it will apply an uplift load on this sill plate, inducing cross-grain bending in this sill plate. And so AWC did tons and tons of tests and to mimic what was seen out in the after an earthquake, and specifically Northridge earthquake, and showed that there are in fact splitting that does occur. There is a mode A, which is shown here and is shown graphically here with a 2x member, and then there is a mode that has a horizontal failure in the sill plate, which is shown here. Now we can calculate mode A, but mode B is a little bit more difficult to calculate. And they also did 3x sill plates as well, I believe. So in order to provide a solution to this, to provide any splitting that was occurred, on the left picture you can see the splitting that occurs with a round standard washer. The plate washer was provided as a solution, which is shown here. And for our highest strength shear wall, we tested it, and this prevented that from happening, the splitting. And it has to be within 1/2 inch from the edge of the shear wall. Now, if someone wants to use round washers, they certainly can, provided they meet this criteria that's shown here. The anchor bolts are designed for in-plane shear. The hold down takes all the uplift, neglecting dead load, and the aspect ratio of the shear wall is less than 2:1. And then it's the limits on the nominal shear capacities are shown here of 980 and 1370. So we have some really good information related to the changes that have occurred, wind and seismic, and we'll come back to this example in a second. But I wanted to mention this because this is not included in your handout, and it's just another resource that some of you may not be aware of, which is the Woodwork software by our Canadian partners, Canadian Wood Council. And they've updated their software for shear wall design to include 2018 IBC, ASCE 716, and based on the wind and seismic provisions for perforated, segmented, and force transfer around openings for various sheathings. And it's up to 6 stories. They have consider rigid and flexible envelope distribution, automatically generates the wind and seismic loads, et cetera, et cetera. There was we have on our website an e-course that Lori and Adam did from CWC on wind solutions for perforated shear walls, where there is a step-by-step design using the Woodwork software if you're interested in knowing what the software can do. And I want to highlight this slide. And Lori, do you want to go ahead and mention something about this since you had a big part in this?
This is our new structural wood design examples. So this is cross-listed for the 2015 and 2018 NDS. We have over 20 examples in here, and they range from very simple ones that include things like determining adjustment factors. And we have several shear wall examples, including the ones we did today, included in there. So it's a great resource if you're new to wood design, if you are studying for the PE or SE, or just want a reference with some completed examples. So it's a free download, and you can check it out on our website. The link is on the slide there, or you can just find it through the publications link on our website, awc.org.
I just sent it to the audience. Okay, good. And the other question that keeps popping up has to do with the shear tables. So I'll go over this, and what it has to do is here we have our nominal unit shear capacities for a wood frame diaphragm, and it states common nails. So we have in this example shown here highlighted is an 8-penny common nail. And also there's a minimum penetration of 1 3/8. Similarly, for our shear wall tables, we have 8-penny common nails or galvanized box nails, and then a minimum penetration of 1 3/8. So in order to use these tables in the wind and seismic provisions, the nails need to meet all 3 of these requirements. In other words, you need to be an 8-penny common nail and have the proper minimum penetration. And we've heard that in the industry that perhaps they may switch out nails. They meet the diameter requirements of an 8-penny, and they meet the minimum penetration, If that's the case, that these tables are not applicable because they are not meeting the common nail requirement, which is longer than 1 3/8, or the galvanized box nail. So it's very important to meet all three criteria. And then Lori, do you want to say something about this table also? And some people were asking, what about substituting for the cooler nails? Where do we go for that?
Right, or gun nails are another one that we get a lot of questions on. So this is ICC ESR 1539 is one of several ESRs, evaluation service reports, that have been published for different fasteners. So the fasteners that are in the WFCM and SPIDWIS tables are assumed to be ASTM F1667 compliant nails. So if you're using something that is proprietary or something that's not in compliance with that ASTM standard, you'd need to use either the manufacturer's data or one of these evaluation service reports. So 1539 is one that is presented for a lot of common power actuated fasteners that you might encounter. And then the way that the evaluation service report is laid out, the tables are in a very similar format to what you're seeing in SPIDWIS, so it makes it very easy to use these alternative fasteners in your designs.
Right. Thanks. So I preempted this, but a question came in regarding the 3.5:1 ratio for wind designed. Is that a change in the wood frame construction manual, someone was saying, from the previous edition?
So it is not a change. The aspect ratio that's been allowed has not changed. However, in 2018, this is the first time you have had to apply the adjustment factors that we talked about, the stiffness adjustment factor or the capacity adjustment factor based on aspect ratio. This is the first time that the WFCM has required that adjustment on both the wind and seismic designs. It used to only be on seismic designs.
Right, exactly. Okay, any other questions? People were asking about the maximum roof height. What is the maximum roof height? And
so for the wood frame construction manual, the maximum mean roof height is 33 feet. If we're looking in our tabulated values for things like table 317A, they assume a wall height and a top plate to ridge height of 10 feet. So that's, and that we did see that we were able to apply some adjustments because our structure was less than that.
Mm-hmm. And you made a good point. It's mean roof height and not to ridge height. And that mean roof height is average grade to average roof height is what that mean roof height is. Is that okay? Any other questions that came in? Did we lose you, Lori?
No, sorry, I'm here. We've got quite a few rolling in. I'm not sure if we're going to be able to answer too many because we're running so much short on time here. There was a question about blocking orientation. So it doesn't matter if you have a blocked shear wall, what is the orientation of the blocking? It is not important. There's not a specific requirement on which way the blocking has to be oriented. You do, however, need to make sure that you meet the minimum penetration requirements on the blocking. So that is something that you may need to take into account. But it does not matter which way the blocking is oriented in your wall.
Mm-hmm. And I don't know if you mentioned this. Someone is asking, is the design example book free? I don't know. Someone asked that.
It is, yeah. It's a free PDF download, so you can download it for free right off of our website.
Okay. And then one question came in, and I think you covered this. Maybe this question was asked before you covered it, but in designing coming up with a capacity requirement for the hold down, do you need to consider the upper floor? Is that, I think you covered it, and maybe that question came in, but maybe reiterate
Yes.
how you do that.
Yeah, so the examples we did were just the first story. So if this was a complete example, we would have designed the second floor shear wall, calculated the hold down requirement on that, and that would have been combined with the hold down requirement for our first floor shear wall that we designed today.
Right. So the hold down here, just say you found the requirement for this wall, but any overturning that's resisted at this location would need to be added to this. Is that what you're saying?
Mm-hmm.
Yeah. Okay. Thank you everyone for joining us, and we hope you've gained a lot of valuable information. You have the PDFs that are available on our website and the publications, and please fill out the survey so we can get your feedback, and we hope you have a wonderful day.